It's probably one of the first big questions we ever ask. I mean, we see it pretty much every single day, right? But the reason why is this incredible story about light, our atmosphere, and believe it or not, the very energy that powers our whole world. So let's get into it. Why is the sky blue? I mean, come on. Every single curious person has wondered this at some point. It seems so basic, doesn't it? You'd think the answer would be super simple. But really, think about it. Of all the colors in the rainbow, why blue? Why isn't it green or yellow? And of course, as soon as you start thinking about the blue sky, your brain immediately jumps to its opposite, right? The sunset. What in the world is going on there that completely flips the color palette on us? Well, as you're about to find out, these two things, they're actually just two sides of the exact same coin. All right, so to crack this mystery, we've got to start at the source. We have to look at sunlight itself. And it turns out that bright white light you see, yeah, it's way more complicated than it looks. You've definitely seen this before, right? You pass white light through a prism and bam, it splits open and shows you its true colors. That's because sunlight isn't really white at all. It's actually a whole team of colors, every color of the rainbow, all bundled together into one beam of energy, traveling all the way from the sun. So, what's the deal? How is red different from blue? Well, it all comes down to something called a wavelength. See, light travels in waves, kind of like ripples in the ocean. And the length of those waves, how stretched out or bunched up they are, is exactly what our eyes interpret as different colors. And that simple difference in wavelength is, well, it's everything. The longest waves of light that we can see, our brain sees them as red. And the shortest, most bunched up waves, yep, those look blue or violet. And honestly, this simple difference in size is the absolute key to this whole puzzle. Okay, so just how short are we talking here? A blue light wave is about 400 nanometers long. Now, a nanometer, that's 1/1000th of a meter. I mean, just try to wrap your head around that. It's a scale that's pretty much impossible to really picture. But here's a way to think about it. A single human hair, just one, is about 50,000 nanometers thick. So we're talking about light waves that are just unbelievably tiny. And that tiny, tiny size is exactly what makes all the difference when that light smacks into our atmosphere. Okay, so think of a beam of light like a perfectly straight arrow. It just keeps going and going, unless, of course, something gets in its way. And when it hits something, one of three things usually happens. It can bounce off, like a mirror. It can get bent, like we saw with the prism. Or, and this is the one we really care about, it can get scattered. And that right there brings us to the main event. Let's call it the Great Scatter. I mean, this is the process that literally actually paints our sky. It's what happens at the exact moment that sunlight comes face to face with all the gases in our atmosphere. So what exactly is scattering? Think of it like a cosmic game of pinball. The light waves come in, and they just start bouncing off all these tiny little obstacles. In this case, the gas molecules, like nitrogen and oxygen, that make up most of our air. And when they hit, they just go flying off in every single direction. The whole thing really breaks down into a few simple steps. First, sunlight dives into Earth's atmosphere. Second, it immediately starts running into all those gas molecules we talked about. Now here's the magic part. Step 3. Those short little blue light waves, they are the absolute perfect size to get knocked around by these molecules. And the result? Well, step 4, all that scattered blue light fills up the sky from every direction, making the whole thing look blue to us down here. Okay, so what about all the other colors? Well, those longer waves, the reds, the yellows, the greens, they're kind of like the big kids on the playground. They're just too big to get easily pushed around by those tiny gas molecules. So for the most part, they just barrel straight through, staying all mixed together. And that's why the sun itself looks like a bright, yellowish-white ball to us. But hey, have you ever noticed this? If you look straight up, the sky is this deep, rich blue. But then you look out toward the horizon and it gets all pale and whitish. What's up with that? What's causing that fade? It really just comes down to one thing: distance. The light you see from the horizon has had to travel through a lot more air to get to your eyes. It's like it's running a much longer race. And by the time it gets to you, that poor blue light has been scattered and then rescattered so many times that a lot of it has already been bounced away from you, leaving the sky looking, well, a lot less blue. Okay,
Now let's take everything we just learned and use it to solve our second mystery, those incredible sunset colors, because it's the exact same science, just a totally different angle.
So here's the key thing to remember about a sunset. When that sun gets low on the horizon, its light has to punch through way, way more atmosphere to reach you. I mean, it's traveling through the absolute thickest part of our atmosphere from our point of view.
And since it has to travel through all that extra air, almost all of that short wavelength blue light gets scattered completely away before it ever gets to us. So, what's left? Well, you're left with the long wavelength team, the reds, the oranges, and the yellows. They can make that long journey, and they get to come straight through to our eyes, with almost no blue light left to compete with them.
And there's actually another little ingredient here. Bigger things floating in the air, like dust or pollution, they're actually really good at scattering those longer red and yellow wavelengths too. That's why sometimes the entire western sky just seems to catch on fire with this amazing, spectacular glow. So there you have it. Mystery solved, right? Blue skies, red sunsets, it all makes sense. But this whole idea of scattering is so much bigger than just a pretty view. It's actually a super critical tool we use to understand our own planet. I mean, think about it. It all comes back to the sun. Sunlight is the engine that runs our entire planet. It's the heat, it's the energy for life itself. So being able to understand exactly how that light interacts with our atmosphere, how much gets scattered away, how much gets through, is absolutely essential for keeping an eye on our climate. And this is where it gets really, really cool. Scientists can point satellites at the Earth and measure the light that's being scattered back out into space. And just by analyzing the different colors and how bright they are, they can figure out all sorts of things from way up there, like the temperature, pollution levels, how much water is in the air. It gives us this incredible health check for the whole planet. And that right there is the big idea I want you to take away from all this. The exact same physics that gives us a beautiful blue sky is what we use to do incredible science. It allows us to track pollution, to follow weather patterns, and to really understand the health of our planet on a massive scale. It's all connected. So the next time you step outside and look up at the sky, maybe you'll see something a little different. Not just a color, but a kind of daily report on what's happening in our atmosphere. And that leaves us with one last really important question to think about. What is the light we see every single day really telling us about the health of our planet?